According to the diagram you see here, the black energy level is identified as the energy level 1, and you can call it quantum number 1. The red circle shows energy level 2, but we call it quantum number 2. And then blue, quantum number 3, green, quantum number 4. In these different energy levels or different quantum numbers, there is a maximum number of electrons that can be accommodated. In the quantum number 1, you can keep 2 electrons maximum. In the quantum number 2, you can keep maximum 8 electrons. In quantum number 3, you can keep maximum 18 electrons. And in the quantum number, you can keep a maximum of 32 electrons. 2, 8, 18, 32. If you think about the arrangement of electrons in an atom, I have another diagram on the left-hand side. What I did was, same thing, I expanded a little bit and taken in this diagram. Can you see on the left-hand side? I have taken only half of the atom. The other half has been removed. Now, if you compare the second energy level, second diagram with the first diagram, I'm going to speak about this electron arrangement in more detail. On the right-hand side, I have mentioned the total number of electrons that can be found out in each and every quantum number, starting from the first outwards. First quantum number, second quantum number, third quantum number, fourth quantum number. And here on the left-hand side diagram, you can see n is equal to 1. Okay, n is a quantum number. N is 1, n is 2, n is 3, n is 4. I explained to you in the last lesson that these energy levels are actually going to divide into something called sub-energy levels. They divide into sub-energy levels. Why do you think these quantum numbers divide into sub-energy levels? It is because when more and more electrons come into an energy level, they begin to repel each other. Electrons are going to repel each other. Therefore, these quantum numbers are divided into sub-energy levels, and in these sub-energy levels, you can keep electrons. I told the first quantum number has only one sub-energy level. And that sub-energy level is called S sub-energy level. Because the quantum number 1 can have only 2 electrons maximum, and the first quantum number has only one sub-energy level, which is called S sub-energy level. It can have maximum 2 electrons. S sub-energy level can accommodate 2 electrons. Because this S sub-energy level comes in quantum number 1, we call it 1s. 1s means S sub-energy level in the quantum number 1. Second quantum number is divided into 2. There's a maximum of 8 electrons. In the second quantum number, maximum of 8 electrons. To keep these electrons, quantum number is divided into 2. Again, in this quantum number, in this energy levels also, the first one, which is closest to the nucleus, is called S. But because it is in the second quantum number, we call it 2s. In this 2s also, we can keep 2 electrons. A sub-energy level can have only 2 electrons. If the second quantum number divides into 2 sub-energy levels, if the one closer to the nucleus is 2s, the other one is 2p. The second quantum number can have maximum 8 electrons. From these 8 electrons, 2 come here, 6 electrons are remaining. P sub-energy level can have 6 electrons. And then third quantum number is going to divide into 3 parts, where again the innermost sub-energy level is called S. Because it is in the quantum number 3, we call it 3s. You know how many electrons can keep in the second energy level, S energy, sub-energy level? There are only 2 electrons. How many? What is the maximum electron number in the third energy level? Which is 18. Now 18 is going to divide among these 3 sub-energy levels. After 3s, we have 3p. We know in 3p, p subshell can have 6 electrons. So 3p has 6 electrons. After 3p, the third energy level, third sub-energy level is called 3d. The third quantum number can have 18 electrons. 2 electrons come over here, 6 electrons come over here. Altogether, 10 electrons are remaining from 18. When 8 electrons are removed, there are 10 electrons. This sub-energy level has only 10 electrons. And then I go to quantum number 4. Because there's no enough space, I take the quantum number 4. This quantum number away from the structure, okay? And this quantum number 4 divide into 4 sub-energy levels. As usual, the closest sub-energy level is called S, but because we are talking about fourth quantum number, we have 4s. 4s can have how many electrons? 2 electrons. Remember, any s orbital can have 2 electrons. Any s sub-energy level. Okay. And we go to p sub-energy level. 4p. 4p can have 6 electrons. Whether it is in quantum number 2 or 3 or 4 or 5 or whatever, p sub-energy level can have only 6 electrons. After phi, we can get here 3d. Here we have 4d. 4d. D can have how many electrons? 10 electrons. And how many electrons are left for the next sub-energy level? From quantum number 4 has 32 electrons. From 32 electrons, we can have 10 here, 10 plus 6, 16 plus 2, 18. If the total number is 32, the remaining electron for the next sub-energy level is 14. And that sub-energy level is called 4f. So this clearly introduces you how quantum numbers divide into sub-energy levels in an atom for better arrangement of electrons. And the story doesn't end here. There's one more level of division in energy levels. First, quantum numbers. Quantum numbers go into sub-energy levels. Sub-energy levels are SPDFC, S, P, D, F. There are 4 types of sub-energy levels. In these sub-energy levels also, there are different numbers of electrons. These sub-energy levels, there are very, 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 very special areas called orbitals. This is the last division, orbitals. Orbitals means, for those who have come newly, what are orbitals? The ones who came last time should remember. Orbitals are special or specific. Orbitals are specific areas in an atom where electrons are found. Electrons are found. And one important point again, an orbital An orbital can have maximum 2 electrons. An orbital can have maximum 2 electrons. So based on this information, what is the information? Electrons are actually arranged or organized in something called orbitals. These orbitals are the areas where electrons are found out. And if you take one orbital can have maximum 2 electrons, not more than 2 electrons. Therefore, can you go to this s orbital, S sub-energy level? S sub-energy level has only 2 electrons. These electrons are arranged in orbitals. An orbital can have 2 electrons. So S orbital, S sub-energy level, because it has 2 electrons, it has only one orbital. I have given it in a different diagram here. From here. And S sub-energy level contains just one orbital. Why? There are only 2 electrons. So it can have maximum 2 electrons. Sub-energy level is S. When you go to P, sub-energy level, P, P can have how many electrons? P can have only 6 electrons. P can have only 6 electrons. Because there are 6 electrons, and they are kept in orbitals, 2 electrons in an orbital. For 6 electrons, there should be 3 orbitals. Here I have shown p orbitals. In p sub-energy level, there are 3 orbitals. You can see here, p, there are 3 orbitals. The first one is known as px orbital. Second one is py orbital. Next one is pz orbital. There are 3 orbitals. One orbital can have 2 electrons. So 6 electrons in p sub-energy level can be arranged in 3 orbitals, each having 2 electrons. Now the next diagram I have drawn here is d orbital. D orbital can have 10 electrons. These 10 electrons are kept in 5 orbitals. D sub-energy level is divided into 5 orbitals. In each orbital, we can have 2 electrons. So altogether, there are 10 electrons in D subshell. Afterwards, we go to F subshell. Do you remember how many electrons are going to be in F subshell? F subshell has 14 electrons. 14 electrons are divided among 7 orbitals. Each orbital has only 2 electrons. This is how we write a complete electron arrangement in orbitals. This knowledge is very much necessary. I hope everything is clear to you. If you don't understand this, you can't do the electronic configuration writing. You can't do electronic configuration writing for any element. Because electronic configuration writing, we discuss in AS, is a little bit different to the energy level, electronic configuration involving in O level. That O level method doesn't work in A level. I hope everything is okay. And can I ask whether this is understood from these children? Slisha, Shabin, Shamara.
I understood.
Okay, Shamara.
I understood it, sir.
Yes, sir, me too.
Okay, fine. If anyone has any question, any doubt, whether you came to the last class or today's class, you can just feel free and talk to me. Okay, I'll be very much happy to explain to you anything that you ask about this lesson. Okay, if you understood that lesson, then I think writing electronic configuration is a little bit easier for us. But then there is one more thing you must realize. It's about the sub-energy level formation in an atom. I explained to you that the first quantum number, if I write here in this manner, first quantum number, second quantum number here, third quantum number here, and fourth quantum number here. Do you remember how these quantum numbers are going to divide into sub-energy levels? Try to remember. First quantum number is going to have one sub-energy level. Second quantum number is going to have two sub-energy levels. Third quantum number is going to have three sub-energy levels. Now, when it comes to fourth quantum number, the distance between the third quantum number and the fourth quantum number is very much reduced. It's a lesser value. But fourth quantum number is going to divide into four sub-energy levels. When it divides into four sub-energy levels, you can see very clearly that the space is not enough to facilitate the breaking of fourth quantum number into four sub-energy levels. Because in the vicinity, there's a third quantum, the third quantum number also. Third quantum number has outermost 3D subshell. When the fourth quantum number breaks into four sub-energy levels, because of this hindrance in the space, because of the limitations in the space, what happens is it breaks into four. The 4s sub-energy level is going to overlap with the 3D sub-energy level in the third quantum number. Third quantum number, fourth quantum number. The lowermost energy sub-energy level in fourth quantum number, which is 4s, 4s has come below 3D. And then other three are okay. 4s, this is 4p, 4d, 4f. This is called an overlap in orbitals. Quantum numbers appear in the sequence of 1, 2, 3, 4. But here, okay, again, I'll do this complete thing, you will understand this better. 1s, 2s, 2p, 3s. Now see, it comes up in an order. 1s, 2s, 2p, 3s. After 3s, we get 4s and 3d. Again, you go to 4s, 4p, 4d, 4f. In between, this 3 and 4 have interchanged. Actually, what happens is 3D sub-energy level of the third quantum number and 4s sub-energy level of the fourth quantum number, they are overlapped. Remember this. With this in mind, we'll see how we can write the electronic configuration of an element. When you write electronic configuration, there are few rules to remember, few information to remember. What are these information? I would rather call them instructions to remember. The first point is this. Electrons are always added to the lowermost, I can say to the lowermost, no, electrons are always added to the available lowermost quantum number. First point. It means When you add electrons to an atom, you have to add electrons to quantum number 1 first. And only after one quantum number is filled with electrons, you go to the second quantum number. That's the first point. Electrons are always added to the available lowermost quantum number. Second one. Electrons are added to sub-energy levels, starting with the lowermost energy, sub-energy levels, lowermost energy, sub-energy levels. In the sequence, S, P, D, and F. You get that point? It means if you go to second quantum number, first electrons come to 2s, and then electrons go to 2p. Afterwards, we go to the third quantum number, first to 3s, and then to 3s. Children here, 3s. I have not labeled 3s over 3s is there, but I have not labeled 3p. Electrons are added to sub-energy levels, starting with the lowermost energy sub-energy level in the sequence S, P, D, and F. Third one. When electrons are added in degenerate orbitals, comma, when electrons are added to degenerate orbitals, comma, pairing of electrons occur only when all the other orbitals have got one electron each. When electrons are added in degenerate orbitals, pairing of electrons occur only when all the other orbitals have got only one electron each. What is this meaning of degenerate? Degenerate means in this diagram, you can see, look at this P subshell. P subshell has 3 orbitals. These 3 orbitals in P subshell have the same energy. They have the same energy. An orbital set having the same energy is called degenerate orbitals. Degenerate orbitals. So these 3 orbitals in the P subshell are degenerate orbitals. And here in this D sub-energy level, there are 5 orbitals. They are drawn in the same level. Why are they drawn in the same level? Because they are degenerate orbitals. Degenerate orbitals. What's the meaning of degenerate orbitals? All the orbitals have the same energy. And this is another set of degenerate orbitals. Degenerate orbitals. Okay. You have the idea about degenerate orbitals now. And what I told was, when you add electrons, when electrons are added in degenerate orbitals, pairing of electrons occur only when all other orbitals have got one electron each. The meaning is this. Example. See, this is a degenerate orbital set. 3 orbitals. I have 5 electrons to add into this. I will do another degenerate orbital set here. When you add 5 electrons, if you add 1 electron, this is 1 orbital, an orbital can have maximum 2 electrons. If you add 1 electron here, 1 electron here, 1 electron here, the way, no, to explain this better, I will take 4 electrons. 4 electrons. If you write 4 electrons in this manner, then this is going to be wrong. Why? What the third point says is pairing of electrons means in one orbital, we have kept 2 electrons. Here also electrons are paired. When these orbitals are filled, they are degenerate orbitals. This orbital is empty. But others have 2 electrons each. No, no, no. This is not going to happen like that. What the rule says is when you add 4 electrons to this p sub-energy level, you give 1 electron to the first energy level, first orbital. Now 3 electrons are remaining. 1 goes to second orbital. Now 2 electrons are remaining. You keep 1 over here, only 1 electron is remaining afterwards. And that electron can be written in the form of a paired electron group appearing in the first orbital. Is it understood? This is wrong, but this is right. Right. If you have these things in mind, we can go to the electronic configuration writing. But still, there's one more thing to explain. And that part is about actually orbitals. I said orbitals are specific areas in an atom where we can have maximum 2 electrons. Now, I use the word specific areas. There are orbitals, S-type, E-type, D-type, F-type. Forget about D and F. We don't discuss about them in AS. In A2, we talk about D, sub-energy level. So let's try to pay more attention to S orbital or S orbitals and P orbitals. In S orbitals, how many electrons can you keep maximum? We can keep maximum 2 electrons. Suppose there's an atom with electrons in the 1s energy level, 1s orbital, or sub-energy, anything you can see, in 1s sub-energy level. You know, the first quantum number 1, contains only 1 sub-energy level, and that is called 1s. This 1s is closest to the nucleus. If you take the nucleus here, 1s has how many electrons? Maximum 1s can have 2 electrons. It means there is an area around the nucleus of an atom, which is called 1s. There are 2 electrons. All right. If I say 1s, there are 2 electrons, where are they exactly? I can draw a circle over here. Can you get the picture like this? To explain this, just imagine you take a mustard seed. Mustard seed. You keep the mustard seed here and take a table tennis ball. Consider this table tennis ball is a quantum number 1. I can insert I can insert the mustard seed in TT ball. Get the picture? Now, where's a TT ball? Okay, this is TT ball. Where's a mustard seed? It is kept right in the middle. Now, if this TT ball is the quantum number 1, there we have 1s orbital. This TT ball is a 1s orbital. In this TT ball, we can have 2 electrons added. But rather than drawing like this, I can draw a line from here to here, another line from here to here, one more line from there to here. Consider these lines as XYZ axis. This is x-axis, this is y-axis, this is z-axis. This orbital has to come, I'm sorry, this electron has to come to the middle. This is called 1s orbital. 1s orbital. There you can have 2 electrons. Let us say there's an atom. This atom has 1s orbital, 2s orbital. It's something like this. Now you take a TT ball, not TT ball, tennis ball. Go to the picture, the imaginary picture I was asking you to remember. First, the nucleus, which is a mustard seed. Mustard seed is kept in a tennis ball, a TT ball. TT ball is smaller than the tennis ball. Now you keep this TT ball in a tennis ball. This tennis ball is the TT ball is 1s orbital. Tennis ball is a 2s orbital. 2s orbitals also can have 2 electrons. So 1 electron here, 1 electron here. If I draw the 2s orbital, I have to draw a bigger circle. This is 2s. This 2s has 2 electrons. However, if I take this 1s orbital and 2s orbitals both in an atom, then we should be able to draw first XYZ axis, and then I can draw a smaller circle or small circle for the 1s and a bigger circle to show the 2s orbital. So likewise, I can say s orbitals are spherical orbitals. S orbitals are spherical orbitals. Now I can go to the next level of orbitals. You remember now, we have a nucleus. Nucleus is next to, okay, that's the first energy level next to the nucleus. This is 1s. And then we go to the second quantum number. It has 2s, 2p. I talked about 1s and 2s in the earlier diagram. 1s is small, 2s is bigger than that. So we can keep 1s and 2s together around an atom, the way how we can see here. Now I go to the next one. Next one is p orbitals. How are we going to organize? Remember, I told you in my lesson earlier that p orbitals are identified how? Px orbital, py p orbital, pc orbital. I'll write something over here. These p orbitals are degenerate. Degenerate orbital, it's given over there. These p orbitals are dumbbell shaped. Dumbbell shape. How many orbitals are there? 3 orbitals. They are dumbbell shape. So this px, I can show like this. This is a shape of px. Px has 2 electrons. 1 electron can be here, 1 electron can be here. And then we go to py. Py is also dumbbell. We can have 2 electrons in py. And then we go to pz. Pz is another dumbbell. This dumbbell can have 2 electrons. See, children? 2 electrons here, 2 electrons here, 2 electrons here. Altogether 6. Px 2 electrons are here. Py 2 electrons are here. Pz 2 electrons are over here. Now I have to show how these orbitals are organized. Now, how many p orbitals are there? Px, Py, Pz. To explain this Px, Py, Pz nature, I can draw X, Y, Z axis across the nucleus. The nucleus is over here. If this is X, if this is Y, if this is Z, Px orbital is along the x-axis, Px orbital, where we can have 1 electron here, 1 electron here. This is called Px because it is arranged along the x-axis. Now we go to Py. Py orbital is extending along the y-axis. 1 electron here, 1 electron here. And Pz is extending over here and behind. To explain the 3D nature of this, I just erase these lines. So you can see the 3D nature of these orbitals. See? If I add some colors to this, you can get the picture in a much clearer manner. This green line show orbital, which is extending along the z-axis. So this is called Pz. Okay. This is another orbital. Okay. Is it understood now? Now you will ask about s orbitals. Where are these orbitals? 1s and 2s, they are over here in the middle. Here we have 1s and 2s. And here these are, again, I'll label them. This is 2x. This is 2y. This green one is of 2, how can I say, no, I'll redo it. This is 2px. This is 2pz. And this is 2pz. This is 2py, isn't it? 2py. This is 2pz. Likewise, orbitals organize in an atom in different orbitals of different shapes in this manner. This is a very, very simple illustration of the arrangement of orbitals around an atom, the nucleus of an atom, taking 1s 2s and 2p into consideration. I think you have understood this concept about orbital arrangement around an atom. And in our next lesson, we will see how we are going to add electrons to these orbitals in detail.